Hello and welcome to a lesson on combinations. So what is a combination? Well, like a permutation, it's an arrangement of items that occurs when items are not used more than once. So it's sort of like a permutation. Like a permutation, a combination is an arrangement of items that occurs when items, again, are not used more than once. The difference is with a permutation, the order of the arrangement matters, and with a combination, the order of the arrangement does not matter. So unlike a permutation, the order of the arrangements for a combination does not matter. Okay, so I have a little scenario, two actually scenarios here set up to try to help you distinguish between a combination and a permutation. And then we'll get to some of the math of it in a few minutes, and actually the math part's really simple. It's the how do you make sure you have distinguished between what is a combination and what is a permutation. When does order matter, when does it not? Okay, so we're going to consider siblings, Amy, Bob, and Cal for the following two scenarios. And we're going to call her A and him B and him C. So let's say these three siblings are in the first scenario here. They're racing to school. And how many ways could they arrive first and second? So who wins first place for the race to school? Who wins second place for the race to school? Well, it could be that Amy comes in first and Bob comes in second. Or Amy comes in first and Cal comes in second. Or it could be Bob comes in first, then Amy. Or it could be Bob and then Cal. Or it could be Cal comes in first and then Amy. Or Cal comes in first and then Bob. So what we have here are 6 total options. And what's happening in this situation is if they're running in a race, the order in which they arrive at the school matters, right? Where Amy coming in first, like, let me just show you here. Amy and Bob and Bob and Amy, right? That's the same two people in those arrangements, but the order matters because in one of them Amy's first and the other Bob is first, okay? Now that is an example of a permutation. So this is a oops, still on my highlighter. Sorry. This is a permutation. Permutation. And this is where order matters. Okay, so in the next example, same 3 siblings, but this time let's say their mom is going to be choosing 2 of them to take with her to the store. So just like the last example, you're looking for 2 of them, 2 of the 3 to be coming in first and second in this race, but now you're looking for 2 of these kids for the mom to take to the store. And how many ways can she choose who comes to the store with her? So maybe she chooses Amy and Bob, or maybe she chooses Amy and Cal. Now, would I say Bob and Amy as a second option here? I know that was the third one I had on my other list, but if she chooses Amy and Bob, or Bob and then Amy, does she end up with a different set of kids? No, in this case it doesn't matter the order she chooses the kids, she's going to end up with those 2 kids at the store. So this is a case where order doesn't matter. So we're not going to count this Bob and Amy as a separate thing, okay? So Amy, Bob, Amy, Cal. I can't put Bob and Amy again. I could put Bob and Cal. I can't put Cal and Amy again, and I can't put Cal and Bob again. So this time we only have 3 total options. Okay, because the order doesn't matter, we're not going to count the rearrangements as separate things. So this is an example of a combination. So in a combination, okay, order doesn't matter. And what happens in a combination when the order doesn't matter, if you're looking at the same groups of things, so both scenarios, the total group of people involved was 3, and both scenarios you were choosing 2 out of the 3 for something to happen. But the number of permutations was 6, and the number of combinations was 3. So if you have the same group that you're choosing from and items that you're choosing, if those numbers are the same, the number of combinations should always be smaller because we're not going to count those duplicates. So order doesn't matter here. Okay, so let's try to read through a few more examples. In these next few, we're not going to be doing any math or calculations. I just want to make sure we can distinguish between a combination and a permutation. And then when we get to the math part, you'll see, again, that it's actually pretty simple. Okay, so Let's distinguish. It says in number 1 here, 6 students are running for student government president, vice president, and treasurer. The student with the greatest number of votes becomes the president, second highest gets vice president, and the student who gets the third largest number of votes is going to be the treasurer. And how many different outcomes are going to be possible? So we don't actually have to calculate that. I just want to know, is this a combination? Is this a permutation? Does the order matter? Well, here we have a group of 6 students running for student body. Does the order matter in which the number of votes comes in, or does the order matter in which they are selected for president, vice president, treasurer? Absolutely, right? The largest number of votes, that's the first person. That matters. So this is going to be an example of a permutation. Order matters. Okay. How about the next one? We have 6 people on the board of supervisors for a neighborhood park. And again, it's 3 people being selected here, just like the last one. 6 students and your president, vice president, treasurer, 6 or 3 people from the 6 being selected. But here it says it's going to be a 3-person committee needed to study the possibility of expanding the park. How many different committees could be formed? Combination or permutation? Does the order matter? When you pick your 3 people, if you picked Bob, Amy, Cal, or you picked Cal, Bob, and then Amy, are those different committees? No, they are the same amount of people, so those wouldn't be 2 separate combinations there. So or arrangements there. So we're going to call this a combination. The order doesn't matter. Okay. How about number 3? How many ways can you select 6 free DVDs from a list of 200 DVDs? Okay, when you pick the 6 DVDs, does it matter which one you pick first versus which one you pick last versus which one you pick in the middle? Nope, because you're going to end up with the same 6 DVDs no matter what. Again, an example of a combination. It doesn't matter here because being the first DVD picked isn't any different from being the last DVD picked. Okay, you're just in a group of DVDs, just like in a committee. How about number 4? In a race which there are 50 runners and no ties, in how many ways can the first 3 finishers place? Does the order matter here? Is there a difference between the first one picked and then the last one picked? Well, absolutely. Because there's a big difference between coming in first in the race and coming in 50th in the race. So here the order does matter, which means this is a permutation. Okay, so generally, if it's, you're slapping a label on something, or it's first, second, third, president, vice president, treasurer, the order matters. You're looking at a permutation. If it's just a committee, you're choosing a group of things, and it doesn't matter what is chosen or who is chosen first versus second or third, that's going to be order not mattering. That's going to be a combination. Okay, so now to the math part of this is actually, again, pretty simple. Just like we have a formula for permutations, we have a formula for combinations. So the number of combinations of R items taken from a group of N items is going to look like this. It looks very similar to the formula we had yesterday. Yesterday we said NPR, when you're looking at the number of permutations of R items from a group of N, that we would have N factorial on the top and then N minus R factorial on the bottom. We still have N factorial on the top, we still have N minus R factorial on the bottom, but notice there's an extra R factorial in the bottom. That's because we have to divide out those extra duplicates. Okay, those duplicates have to be divided out because we can't count the rearrangements as different things when order doesn't matter. Okay, now the formula is here and we should be able to absolutely use the formula, but in the same way Desmos will calculate combinations for us, it will calculate permutations for us. So in Desmos, remember, we wanted to go to functions on our keyboard, and then we go to stats, and then we hit the NCR button, and then in the parentheses we're going to put N comma R, and it's going to make the calculation for us. Okay, now let me just take you back to the front here. So again, this first scenario we looked at, this was a permutation. So this was a permutation and we were choosing two of the siblings of the three to see how they placed in their race to school. And this was a combination where we were choosing two out of the three to go with the store, or go to the store with mom. Okay, so Desmos would calculate both, and we can just kind of verify our work here. So we go to functions, we go to stats, and the first one was permutations, and it was 2 from a group of 3, so 3 comma 2, and there's our 6 options that we had written. And now we can go to the same place, function, stats, and then it's NCR. So if it was 3 and 2 again, because it's combinations instead of permutations, we only have the 3 options. Okay, so Desmos did both these. This was a permutation, and the calculator showed us 6. This is a combination. Calculator showed us 3. Okay, so now let's practice using the calculator. Back to the back here. So example 5. A 3-person committee is needed to study ways of improving public transportation. How many committees could be formed from the 8 people that are on the board? So again, the order doesn't matter when you're making this committee. Whoever's chosen first, second, it doesn't matter. They're going to be on the committee. So this is again a combination, and for this combination we are choosing 3 people from the group of 8 people. So choosing 3 of the 8. So we're going to put this into Desmos, and it's going to tell us, oops, let's get rid of that. If we're going to choose from 8, 3 of those people, that there are going to be 56 different committees. So different possible committees. Okay. Number 6. In poker, a person is dealt 5 cards from a standard 52 card deck. The order in which the 5 cards received doesn't matter. How many different 5-card poker hands are possible? So the order in which you receive the cards doesn't matter. You end up with the same 5 cards. So we're looking for how many combinations are there of receiving these 5 cards from the 52 cards there are total. So back to calculator. This was 52, choosing 5. That is a whole bunch. 2,598,960 different poker hands are possible. And that's why, I don't know, I don't play cards a lot, but if you do play poker, or if you know anything about playing cards in general, that's why it's really hard to get some of those super good winning hands, like, because there are over 2 million, 2.5 million possibilities. What are the odds of you actually getting, you know, a flush or a full house or one of those really good ones, right? Okay, so in the next couple of examples, what we're going to do is combine our combination formula with the counting principle, and I'll show you in this next one. So it says that a zoo has 6 male bears and 7 female bears. 2 of the male bears and 3 of the female bears are going to be selected for an animal exchange program. How many 5-bear combinations are possible? So we have to do 2 things here. We're looking for 2 combinations. So first, we're choosing female bears, or actually male, it doesn't really matter, but we're going to choose male bears, and we're looking for a number of combinations for just choosing the male bear. And it says that we're going to choose 2 male bears out of these 6 male bears that are available. So there's going to be a certain number of combinations available just for choosing the male. And then when we go to choose the female bears, okay, we're going to look for a number of combinations there as well. So it says we're going to be choosing 3 of the female bears from the 7 females that were possible to choose from. So there's a number of combinations for choosing the male, there's a number of combinations for choosing the female. If I want the total number of combinations, just like if I wanted the total number of outfits, and I had 3 options here and 5 options here, I have a certain number of options here, I have a certain number of options here. The counting principle says I can multiply to figure out the total number of outcomes. Okay, so now I'm going to use my counting principle to multiply, right? This is counting principle. It says multiply the number of options for each event, so selecting the males, selecting the females, to get the total number of outcomes. So we can see how this is combining our counting principle and our combinations. So we go to our calculator, and we're going to choose from 6 bears, we're choosing 2, that's the males, times, let's get combinations in there again, this time 7 and 3. So all together, 525 5-bear combinations. So 525 bear combinations. Okay, let's try that concept again. So it says you're having a dinner party. You have 10 different bottles of soda and 8 different bottles of juice. If you were having a dinner party, my guess is you're not choosing from soda and juice, but I had to try to make this somewhat appropriate. So you want 4 bottles of soda and 2 bottles of juice, and how many ways could you choose your beverage? So again, you've got 2 different choices, just like you're choosing from pants and shirts to make outfits, right? We want to choose from bottles of soda and bottles of juice. So let's go soda first. Okay, so when we go to choose the soda, it doesn't matter the order we choose the soda, we're going to end up with the same 4 bottles. It says we're going to choose 4 bottles of soda, and there are 10 different bottles of soda to choose from. So we're going to choose 4 of the 10, and then we're going to go choose our juice. And for the juice, it says we want 2 bottles, and there were 8 bottles to choose from. And then the counting principle says I can multiply the number of combinations of each, multiply the options there, multiply the options there. That counting principle is going to give us the total, then, number of options. Counting principle. So all together, and I can just edit in here. This was 10 and 4. And over here is 8 and 2. 5,880. So 5,880 beverage choices or beverage combos. Okay. Alright, so I think hopefully this is coming together for you. I've got one here if you want to pause the video and give it a shot. You may, if not. Obviously I can't force you to do anything there, but what's happening is, so at a Chinese restaurant, dinner for 8 people consists of 3 items from column A, 4 items from column B, and 3 items from column C. If items A, B, and C have 5, 7, and 6 items respectively, how many different dinner combinations are possible? So we're making 3 choices. We're going to find the number of combinations for each of those choices, and then multiply to get the total number of combinations. So let's choose first an item from column A. So from column A, we're going to choose 3 items, and there were 5 options. So we're going to choose 3 of the 5 options. And then for B, from column B, 4 items is what we're choosing out of the 7 that were available. So we're choosing 4 out of 7. And then let's go to column C. So column C, we want to choose 3 items, and there were 6 available. So we're choosing 3 out of 6. And then our counting principle says I can multiply the number of options for each of those events to get the total number of combinations. So we need here 5 and 3, and then here 4 and 7, and then I'm going to need to get NCR in there once more. Oops, I need to put multiply in between those. 6 and 3. And I just want to point out again that these are combinations, right? The order in which you choose your 3 items from column A, it doesn't matter. Those are the 3 items that are going to be plopped on the table. It doesn't matter if you ordered chow mein and then rice and then orange chicken. Okay, those 3 items are showing up on the table. Okay, so altogether it looks like 7,000 dinner combinations. which is crazy. That's why people get so indecisive at restaurants. Okay, so hopefully this makes sense. You've got some practice problems to try it out, and if you find yourself struggling, as always, I am here to help, so just reach out. All right, guys, take care.